Hi, I'm Art Wiggins. Welcome to another episode of The Art of Physics. And this one is going to be fun. I mean, you think the others can be fun too, but this one's going to be even more fun. Because this time I have a guest. And my guest is Lewis Tann, who is a man of many talents, some of which include toys. And many of them have physics implications. Lewis, welcome to the program.
Oh, thank you, Art.
You betcha. So we have a number of toys to show today. I think the first one is one that has to do with a pig. We brought along a pig. And so David, I think, ran some things about that earlier. So if David introduces that pig at about this point, then you can see what the pig is about. Okay. Now, we have a toy to show you that involves a pig. Now, there are certain prohibitions against pigs and so forth. So maybe I should be politically correct and grab this pig and just get it out of here. So okay. Hey, wait a minute, I can't seem to get it. What's the problem? Can you see me grabbing that thing? But there doesn't seem to be anything there. It's a physics trick. It's a toy for sure, but it's a physics trick in the sense that there are mirrors involved. And these mirrors are such that there's one underneath here, a concave mirror. There's another here on top of it, a concave mirror. And if you trace these things, which you can do through physics, you can trace them to figure out, not easily, but you can trace them and figure out where the image shows up. And the image shows up where there isn't anything really. The pig is all the way down below, the image is up on top, and it's a real image in the sense that you can grab it. And of course, it's not real in the sense that the pig isn't there. So you got an object and you got an image. Physics is able to sort these things out. But of course, they're also toys and kind of fun. So anyway, piggy, this little piggy went, I don't know where. Okay, now that you've seen the pig in its natural habitat, I should say, then we have a few other things we want to show too. Lewis, what are we showing next here?
Well, I think we've got a top that wants to spin forever.
Ooh, this guy.
It, for all appearances, seems to want to be defying the laws of physics.
Hate to have that happen.
But when we look at it a little more closely, we'll find that deep down inside the base, there's a battery and a little electrical switch, and it keeps sending an impulse through an electromagnet to keep that top spinning, and that should be good for about a week.
Wow. Spinning top, round and round.
And from that, we had a couple of other devices. Another one that's a magnetic toy in terms of Newton's cradle.
Oh, that's this thing.
Mm-hmm. Or modeled on Newton's cradle, at least.
So if you try to do something like this, you've seen the Newton's cradle before, I suspect. Try to do this, then it looks sort of like Newton's cradle, but let's see if it does the other things Newton's cradle does, and that's if you take two, does it make two? Oh, no, it's a lot more confusing. And Lewis says that if you put this little gadget inside there in just the right way, that may make it... Do I need to hold it?
No, you may get an oscillator, or you may shoot the magnet right out.
Really? Let's see if we can shoot the magnet out. Can you see this okay? Is this wild? These toys are very entertaining. So maybe I can try three. What does three do?
There you go. You do have actually the Newton's cradle of the more classical form there.
That's this guy.
Mm-hmm.
Now let's see, is this the best way for you to look at that one? Camera 3?
This one out.
Jason will like it this way. There it goes. So now we have... Whoa! Jeez. I'll be darned. Scared him right out of his skin. Nice. So now we have conservation of momentum and almost conservation of energy going on here. Now, those are fun. Now, how about this way? Have you ever tried it this way? That's always good. And then, of course, there's the pièce de résistance. That's not very interesting, though, is it? How about this one? That's not bad. Now, let me give you an illustration. Our director, David, is having a bad day today, and I think David is feeling inside kind of like this. What do you think? Is that about right? Not too bad.
So, you know, we look at these toys, and in preparation for this opportunity to speak with you, thought a little bit about toys and where they've come from. And, you know, some toys go back over 4,000 years.
Wow. In a way, that's not surprising, I suppose. Toys are interesting things. They're fun. People like to have fun.
Well, early toys were really created for educational purposes, to motivate children to learn about things that they would experience as they got older and grow up. But that doesn't apply so much to what we have here. Certainly the physics side of these toys are educational, but in fact, from a collecting viewpoint or just an acquisition viewpoint, a lot of this is just entertainment. It's things that are just fun to have around and to experience the various phenomena.
So these are good for amazing grandkids and maybe a little more.
Absolutely, absolutely.
That's a good way to go. What's the blue thing here? Ooh, that's neat.
I don't know how well this will show up, but this is a little bigger than a typical marble, and in fact is modeled after something that NASA did in taking pictures of the Earth. And when they got all put together, somebody designated the project as the Blue Marble Project. And this particular marble does have printed on it or painted on it all of the land masses of the Earth.
Wow. And the blue represents the oceans, I suppose.
And the blue is the oceans.
Right. Mm-hmm. Very nice. So this blue dot on which we live, that was something Carl Sagan used to talk about.
That's true.
Blue dot.
That's true. And from space, the astronauts that were traveling to the moon, one of the first trips to the moon, I'm not sure, that could have been 7.
I think it was.
Were looking back at the Earth and happened to have a very clear picture of it, and they shot a beautiful view of the Earth, which is probably one of the most famous views that exist right now, and that's also been included as part of this Blue Marble project.
I think that was the cover photo in, what was it? What was the name of that called? The Whole Earth Catalog?
Yes, I think it was.
Wow.
Could have been.
Could buy the entire Earth, do you think, in that catalog?
Probably not. Probably not.
Darn.
There's a couple of other interesting globes here.
Oh, yeah. Let's see these things.
Here's one that's suspended. It's not horribly stable right now, but is magnetically suspended. There's a magnet, electromagnet up here, and you can see it's just hanging in space, nicely balanced in terms of the weight of the globe and the forces, the magnetic forces.
Right. Just enough to hold it in place.
Mm-hmm.
Seems like good material for a physics problem. How much magnetic force would it take to suspend this globe because it has a certain weight?
Mm-hmm. The physicists that designed this have advanced quite a bit further now, and instead of putting globes in here, you can actually put other objects in here which you can attach a magnet to, and other things, automobiles, space rockets.
Right, so they would turn.
And they would spin in a base like this. So
that's kind of, in a way, it's similar to the 3D views that you get, which are all done electronically, computer-wise, that will show you views from different angles. But that's all done with renderings of one type or another. This one is reality. So that's neat. So that's purely electromagnetic, so it's got to be plugged in.
Yeah, this one is the only device on the table that literally has to be plugged in, and of course the perpetual top, which is running off a battery.
But the battery's inside the black puck.
Inside.
Okay.
Typically, from an interest viewpoint, I look forward to devices that really don't require any electrical sources. But these happen to be examples that do.
I suppose not requiring electrical sources. Maybe they could run with, again, an outside energy source, but one which is so ubiquitous that we don't even think about it so much.
And we actually, that segues right into this piece. Hopefully I don't stop its function, but there is a device that has no external connections to a power source.
No battery.
No battery.
Lucite base, and you can see in it, you can see there's no battery inside.
But this particular globe has a couple of very unique features to it. There's a photocell. It's actually covered on the top with the image. But there's a photocell just below that image that's extraordinarily sensitive, and it's picking up ambient light.
So these hot lights are good for something besides making us sweat?
Absolutely.
Oh, that's good.
They're making the world turn. And that energy is then being used to drive a little motor in here. But then there's one more piece that's very unique, and that is, in order for this to turn, somehow there's got to be an action and a reaction.
Right.
The globe itself has a plastic shell around it, and there is a liquid inside that shell which the globe is turning inside of. So it's extraordinarily low friction. The electric motor is attached to a iron bar, the purpose of which is to align with the Earth's magnetic field. That's the stationary point that the motor is using as its reference to react against to turn the globe.
Wow. So the Earth's magnetic field gets into this, as well as ambient light, which could be sunlight, not necessarily. In this case, it isn't.
Yeah, but either way.
But either way. So it takes light, really, and magnetic field to make that run. And yet it looks like world's simplest thing.
But very, very sophisticated in terms of the design. And,
yeah, a lot of stuff going on inside there.
And in fact, the piece that's in there that gives the reference point is not unlike
the compass.
The compass.
I was just thinking about the compass, because the compass, after all, is an indicator about the Earth's magnetic field. And we did a little segment earlier, because the camera couldn't see the compass real well sitting on the desk. So we actually had a little piece about the compass and the significance of the compass that maybe was not quite so obvious. The Earth's magnetic field had an impact, a big impact on science. So maybe if David segues to that and intersperses that with the other things of this discussion, it will make some sense. David, will you do that? Here's another one for you. Now, this is hard to conceive of as being so scientifically accurate and necessary to the development of science, and yet, oddly enough, it is. This, of course, is a compass. And the compass is something which we're all familiar with to whatever degree. But can you remember when you became familiar with a compass and you began to realize that as you look at a compass, this needle pointing north stays pointing north regardless of how you turn the thing? I can't turn it now or else it's going to get out of camera range. But if you turn the compass, what happens? Well, the needle still points north. Okay, well, that's interesting. First time that ever happened to you, I'm sure that you thought, wow, that's really neat. Okay, next. Guess what? It didn't work quite that way for somebody else. Our good friend Albert Einstein, at one point when he was a youth, probably 5 or 6 or so, became ill. And in order to try to help him work through his illness, his father took out of his pocket a compass and said, look, Albert, look at this compass. Albert looked at the compass, even in his illness, and was impressed by the fact that the needle always pointed north. Well, fine. That stayed with him far longer than it did any of the rest of us, because the idea of action at a distance, the idea of something happening which doesn't have any contact with this needle, is making the needle move. And that continued to prey on his mind for a long time. Now, did that lead directly to the development of relativity and quantum theory? Not quite directly, but you know how these things have their humble roots. That's part of the humble roots. Okay, so the Earth is involved. Einstein was involved. Einstein gets into a lot of things these days, you know. But actually, there's something that goes even beyond Einstein. Einstein, I think, if you think about him as being Mr. Science, I mean, he epitomized science. But, and maybe physics and maybe even mathematics to some extent. But this program is about the art of physics. And so is there some art that we can get involved in this, as well as the physics? And to that effect, Lewis has brought along something which is an absolutely fascinating piece of artwork. Now, this artwork, I'm going to move things out of the way because I want the camera to be able to get this. Get it close enough that Lewis can touch this thing, because Lewis does a better job of this than I do. I think we're both going to play with it to some extent, but...
So this piece is a sculpture that was created by an artist named Yaakov Agam. And this particular piece is referred to as the beating heart. And to get a sense of what happens in terms of, there's a little bit of an idea of what happens when it starts to beat. But more interestingly, if we start out with this and steady it, we can look at it as basically being a three-dimensional static sculpture.
Right, it just sits there. But it's three-dimensional because it goes in all directions.
Right.
However,
as soon as you impart just a little bit of energy to it, it starts to move and becomes a four-dimensional piece, the fourth dimension now being time.
I guess we're back to Einstein in a way, aren't we? Because he certainly represented four dimensions, the fourth being time. Wow, that one is, it's beautiful to look at.
Conceptually, each piece is just a piece of wire that's been joined together and on itself and put into a particular form or shape. And obviously, depending on the size, the frequency in which they oscillate are all going to be a little bit different.
Right. Wow.
There are 9 pieces here. And while not particularly adept at doing this, there is the ability to change the shape of the design and have it sit in a little bit different forms. They won't all oscillate the same because the pieces will start hitting each other. But you can see now here we've got a little different curve of the heart.
Yes.
Maybe a distorted heart, if you will.
Right.
What's interesting is...
And they're kind of like rocking chairs too, aren't they?
What's interesting is... Yeah, that didn't quite drop, but what's interesting is that there's another mode in which this piece will operate by turning it over 180 degrees. You get a totally different...
That is so lovely. Now that actually has another dimension besides, because it makes sound, because it's sitting on this desk and it's making noise as well, which is an interesting noise.
It is.
You could probably make different noises depending on what it was sitting on.
Perhaps, although I will tell you honestly, have not done a lot of experimenting with that.
I don't think you're retired enough to have done enough experiments, Louis. Why, I have time immeasurable to experiment with things.
Well,
that is lovely. Wow.
So each of these different toys that we have on the table today have pretty much come from different places. We stumble on them in some of the magazines, scientific type magazines. Occasionally we'll be in a store that has technology type devices. In discussing this with my wife, we have to talk about the fact that how does this fit in with the definition of what a toy is, and I've had to back off a little bit and say, well, some of these things are just gadgets.
But the difference between a gadget and a toy is sometimes quite minor, isn't it?
Perhaps.
Yeah, perhaps so.
Perhaps.
You know, speaking about Louis and his lovely wife, I love to Google people to find out what they're all about. So I have a graphic I found on Google. When I Google you, applied that to Louis, I found an interesting picture that shows Louis and his lovely wife. And what a nice, attractive couple you guys make. It's really amazing.
Well, thank you.
Yeah, that was really good. So I Googled that, and when Louis and I were talking about this, Louis said, well, you know what? He said, I'm going to turn the tables on you. He says, I'm going to Google you and see what I get. I thought, oh my gosh, you know, what is out there about Art Wiggins that you could Google? So I supplied him with something from 1978. And it's me talking about the size of the universe. And it's a little hard for me to do it because I only can reach so far. But I happen to have a string, and the string, it was actually a yarn, and it went from red, orange, yellow, green, blue, indigo, violet from one to the other.
Covered the spectrum.
I tried to do it. That was the best that I could do. So if you're going to turn the tables on me, I guess I'm going to have to humbly accept whatever it is that he asks.
Well, before he asks, I just want to observe that when I went through and Googled, there was a lot of references to Art Wiggins. You did your undergraduate at Notre Dame.
I did.
You graduated from U of M.
I did.
You've had approximately 4 distinctly different jobs.
Yes, I have.
The longest one was 37 years at Oakland Community College.
37 years.
And 37 years teaching physics.
Yep.
In all aspects of physics.
You bet.
So what I want to know, though, is why is it so many students have gone online and rated you 5 out of 5 and phenomenally entertaining?
Those are extra credit projects, Louis, that I was hoping that they would... in fact, I didn't know about that, but thank you for telling me that. It is interesting. You know, teaching is very rewarding. So if they get something out of it, all the better, because I'm certainly getting something out of it.
Well, I have to tell you that along with the ratings, it was pretty consistent that people recommended that if you could get into one of Professor Wiggins' classes, it would enhance your education significantly.
Well, I certainly thank them for thinking those kind of things, but, you know, this is part of the last 2 minutes that we're going to run our way through this. This is part of my deal, because when you told me you were going to reverse the tables on me, I thought, you know, what am I really about? What is it that I'm really after? And what I came up with was a concept that's actually a Jewish concept. It's a concept called tikkun olam. And what tikkun olam means, and I'm sure Louis knows this, is to repair the world. I try to do my tiny little bit to make the world a little bit better. And I'm still working at it because I'm not sure it's getting any better. So, you know, what's my biggest failure? I don't see the world getting much better, Louis.
Well, I think that each of us can only do our small part, and it takes many of us to change the direction of the world. And without a question, your passion as a teacher, as an instructor, as an author, which we didn't refer to yet, I think, how many books have you?
Well, I got 4 in print right now.
As an author, and now as a communicator and a teacher of physics through this media, I think clearly is making a difference.
Louis, thank you for the kind words, and thanks for helping me out, because this is part of what this is happening. Making toys, making fun, that's going to make the world better. Louis, thank you so much.
And thank you.
So this has been another episode of The Art of Physics. I hope you enjoyed it as much as we did. Thanks so much, and until I see you again, I'm Art Wiggins.